Hello everyone, and welcome back to this episode of the ICP Developer Journey. In today's episode 4.6, Motoko Level 4, we're going to be diving into the final Motoko module in this Developer Journey series, and we'll be talking about Motoko concepts and components, including mutable and immutable state, local objects and classes, message inspection, and errors and options. So let's dive right into it. So every actor in Motoko uses an internal mutable state. This is private and it cannot be used or shared by other actors. This is a core design component of Motoko because it allows mutable data to always be private and it is not shared publicly or remotely. And if it were to be shared or executed remotely, that would pose a possible security risk. So this is an intentional design of the Motoko language. The term mutable refers to something that can be changed or altered, and the term immutable refers to something that cannot be changed or altered. So let's take a look at the difference between mutable state and immutable state by looking at immutable variables versus mutable variables. So in Motoko, an immutable variable, so one that cannot be changed once it's been defined, uses the let syntax. So in this example here, we can see let text immutable. It's defined as type text, and then the value of that variable is defined as text developer journey. And then the same for the second example of num immutable. It's defined as a type nat, and it has a set value of 50. So neither of these variables are able to be changed once they've been set. In comparison, mutable variables in Motoko use the var syntax. So in this example, we have var pair mutable, and this defines a variable that has a pair of values. In this, they are going to be the first type of text and then the second of type nat, and then they are defined as the same name, text immutable and then num immutable. And then the second one, variable text mutable, is just defined as type text. So if we wanted to update the values of these mutable variables, so the two that are defined using the var syntax, we can use the assignment operation of semicolon equals sign, and this works for all types. So here we can see if we wanted to make a variable called text mutable, so that's this one here, this defined as type text, we can use this assignment operator and we can change it to equal a string of whatever languages we want instead of the value it's set to here, which is it's set to whatever text immutable equals. And so in that instance, it would be equal to this text immutable developer journey value. So here we're going to use this assignment operator and change it from equaling the developer journey value to XYZ. And then we can do the same with the pair mutable variable that we defined that had type text and type nat for the two variables that are stored in that pair. And we can use that assignment operator to change the text of those as well. It's worth noting that an actor processes calls by performing updates on its internal mutable variables using the same syntax as shown above. So now let's take a look at how to read data from mutable memory. So when data is read from an actor state, each mutable and immutable variable will look alike. However, they are going to behave differently. So for example, if we take a look at the first code snippet that shows an immutable variable using the let syntax, it looks almost identical to the second code snippet. The only difference is the second example is using that var syntax, so distinguishing between immutable in the first example and mutable in the second example. So while in the context of these two snippets, it doesn't seem like there is much difference between the code, but these two variable types have much different meanings, especially in the context of larger projects or programs. The immutable variable definition that's using let, in that program, each occurrence of the variable equals 0, and if you were to replace each occurrence of that variable with the value 0, it would not change any of the program's logic or behavior. However, in the mutable variable that uses the definition var, each occurrence of the variable is determined by that mutable dynamic state of the actor. And so each occurrence must read and produce the current value of the memory call for variable X. Let-bound variables are more fundamental to a program. To demonstrate why, let's consider the following example where the var-bound variable uses a single element, which is a mutable array, and that itself is bound using a let-bound variable. So in this instance, instead of declaring X as a mutable variable that initially holds the value 0, the variable Y is used, which is mutable, and it defines a mutable array that holds a single entity. It's important to note that the read-write syntax for mutable arrays is not as readable as var-bound variables. Therefore, reading and writing to variable X will be easier than reading and writing to variable Y. When we're talking about arrays, it's important to also note that the Motoko standard library provides an array library that can be used for both mutable and immutable arrays, and this can be imported into your Motoko programs with the import array and then defining the array library from the Motoko base library. So talking a bit more about arrays specifically, before we talk about mutable arrays, let's first take a look at immutable arrays, which share the same syntax but do not permit updates. So for example, if we consider this code snippet, we have an array that is defined as let A. It has type nat, and this array has 3 values in it. Then if we want to read from this array, we just use the traditional bracket syntax for the desired index that we want to read. So then for this second example, we can define a second variable called X, and we can say that we want to pull A and then index 2, so that would be value 3 in this instance, and then A index 0, so that would be 1 in this instance. And this example is just adding the 2 values together, so that would be adding 3 plus 1, and so X here would end up equaling the value of 4. In comparison, mutable arrays by design do not share their mutable state, and so a Motoko type system defines the firm distinction between mutable and immutable arrays. This distinction impacts the language's types, subtypes, and the language's abstractions for asynchronous communication. Mutable arrays cannot be used in place of immutable ones, since the Motoko definition of subtyping for arrays distinguishes cases for the purposes of type soundness. In the context of actor communication, immutable arrays are safe to send and share, while mutable arrays can only be shared in messages and have non-shareable types. So to define a mutable array, we can define it in the same way that we defined the immutable array, but instead we are going to include the var syntax within the array's values. So here we have let A defined here as what would initially look like an immutable array, but then we have var nat and var our array values. And so these are the distinctions between the syntax of the mutable array and the immutable array. In this array, there are 3 values that have the type nat. These 3 values can be updated, however, the number of entries cannot. So this array can only ever hold 3 values, but we could update these values to be 5, 6, 7, or whatever other number values we wanted to, but they would all have to be of type nat. It is possible to declare a mutable array that has a dynamic size, such that the numbers of the entry within the array can be updated. And to do that, we can use the array init syntax. And so in this, we first are defining a variable for the array size of type nat, and then we are defining our array with the same var nat to define the type, and then instead of defining a bracket list, we are using this array.init using type nat, and then using that variable size, and then this instance we have an initial value of 5. And so then if we wanted to update this mutable array, we can use that assignment operator syntax that we used before, this := and we can use that to replace whatever index value that we've defined here. So for example, we can replace index value 2 of this array with the value of 42. So in the context of subtyping with mutable values, there are two very important notes. Subtyping does not permit mutable values to be used as immutable values, and subtyping does not permit a mutable array of type var_nat to be used in places that expect a mutable array of type nat. This is because mutable arrays require different rules for subtyping. In particular, mutable arrays have less flexible subtyping definitions, and so Motoko does not allow mutable arrays to be shared across asynchronous communication, since the mutable state of the actor is never shared. Moving on to local objects and classes. So Motoko objects encapsulate the canister's local state by using var-bound variables. This packages the state with any public methods that are used to interact with the state or update it. As we mentioned before, any objects that include a mutable state are not shareable. So to provide a workflow that overcomes that limitation, an actor's objects are able to be shared, and they are always able to execute remotely. Actor objects and classes communicate exclusively with Motoko data. In comparison, local objects and classes can pass any Motoko data to another object's methods, including other objects. Local objects and classes are essentially the non-shareable counterpart of an actor's object and class. Classes are going to be defined in Motoko using the keyword class, followed by the name for the constructor and the type being defined, optional type arguments, an argument list, and an optional type annotation for constructed objects. In the previous section, we looked at mutable state declarations of private mutable state using var-bound variables and mutable arrays, and in this section, we'll use mutable state to implement simple objects. So first, we need to clearly distinguish the difference between an object class and an actor class. An object class refers to the blueprint, essentially, that is used to define a series of related objects with customizable states. Motoko provides a class definition which helps to simplify building objects of the same implementation and type. In comparison, actor classes are when an object class exposes a service. The corresponding Motoko construct is an actor class, which follows a similar design. So now let's take a look at a simple code snippet for a counter object. This is an object declaration for the object counter. And in this declaration, we have just a single object that is called counter, and it has three public functions: increase, bump, and read. And it uses the public keyword to declare each of these as a shareable function. This object definition also includes a single private mutable variable called count, which is defined by the var declaration. So we can see that defined first here, and then we have our three public shareable functions defined afterwards, and then we make a call to the inc or increase and the read functions. By default, all declarations in an object block are private, such as the variable count in this example. So, taking a look further, in that previous object declaration, counter has the following object type, which is expressed using a list of field pairs. So we have our three functions, inc, read, and bump, and then we can see if we go back here, inc is calling that variable count and increasing it by 1. Read has a type nat, and it's calling the value of that count variable, and then bump just has type nat, which calls those two inc and read functions. Each field type includes an identifier, a colon, and a type for the field's content. In the example above, each field is a function, so in this object type definition, each one includes an arrow, which is used to display the type form. The type for the variable count is not included in the object's type, since its presence and information are inaccessible from outside of the object. The inability to access the variable count provides an important benefit. The object has a normal general type with fewer fields, and in return is interchangeable with objects that implement the same counter object type differently without including a field such as count. So to demonstrate that, the following variation of the counter declaration uses the same object type, but it uses a different implementation of the count variable using an ordinary nat value. The object type is interchangeable with the previous example. So here we can see that the variable count is defined as data type nat8 and it equals 0. And if we go back up here, it was defined just as 0. It wasn't defined as a specific data type. And we can see that to accommodate for this data type of nat8, we have a couple other minor changes to the typing definitions for where that variable is referenced in the other functions. But this object type is interchangeable with this previous type that does not define count as a nat8 type. So now let's take a look at object subtyping. In Motoko, object subtyping refers to objects that may have various types. Object types with less fields are typically considered subtypes. An object subtype in Motoko uses structural subtyping, where the equality of two types is based on their structure. Two classes with different names but equivalent definitions will produce type-compatible objects. So to demonstrate subtyping, let's continue using our simple counter example, but this time use a more general type that uses fewer public functions. So here we are defining the object, we're going to call it bump counter. We're defining a variable called c that equals 0, and then we're defining a single public function called bump with type nat, and in this we are just increasing the value of the variable c plus 1 and then returning that value c. The object type for this object bump counter exposes only one operation, which is this public function bump, and it has type nat. This example exposes the most common operation and only permits a certain behavior. You may want to implement another version with more generality, such as our example from earlier that had the 3 separate public functions. Or you may want to implement a type with additional operations, such as a write operation, which would then be defined with this object type. If a function expects to receive an object using the first type of bump nat, any of these versions of the type will work since they are equal to or a subtype of the most general version. If you want to use a function that expects to receive an object that uses an additional operation not included in the other types, such as the write operation, only that type will work. Now let's talk about object classes. An object class is a package of entities that share a common name. For example, we can define an object class for counters that start at 0 by defining class counter, and then in this we can define that variable c that equals 0, the public function inc, which has type nat. In this function, we are increasing the value of variable c by 1 and then returning whatever the value of c is. By using this definition, we can then construct new counters, each with their own unique state that start at 0, such as we can define a variable called let c1 equal counter and then let c2 equal counter. Then we can use c1 and c2 independently of each other. So we can have let x equal c1.inc and let y equal c2.inc. We can also achieve the same results through a constructor function that returns an object. So we could have a function that uses the class counter, which includes that inc function that returns type nat, and then in it define the object that includes the variable c and that public function. Note that the return type of this function is inc with the result nat, which could be named to be used in further type declarations, such as type counter equals inc returning type nat. So in that object class example, it demonstrates how you can initialize counter functions to start with a value of 0. You can also have them initialize with a value other than 0, such that you can pass a data argument to the constructor function, and we can have it be defined as init rather than 0, and this will now reflect the counter value of whatever data argument is passed to it as the initial value. Next, let's talk about Motoko message inspection. So when a canister receives an ingress message that is submitted through HTTP, the canister can inspect and either accept or decline the message before executing it. For example, when a canister receives an update call, it uses the canister method canister inspect message to determine if the message will be accepted. If a canister does not contain a WASM module, the message will be rejected automatically. If the canister is not empty, but it does not implement the canister inspect message method, then the ingress message will be accepted. Canister inspect message is not used for HTTP query calls, intercanister calls, or calls made to the management canister. For more information about this, be sure that you are familiar with the canister development security best practices before using this feature in production, because the canister inspect message method is not a secure way of implementing things such as authorization checks. Message inspection is designed to mitigate some of the denial of service attacks, since it drains a canister of their cycles for placing unsolicited calls that are rejected. Actors can elect to inspect messages and make a decision on whether to execute them or not by declaring a system function called inspect. Using the message's attributes, this function produces a true or false value that indicates if the canister decides to accept or decline a message. If the call traps, it will return a false value. The argument type of the inspect function is going to depend on the actor's interface. A formal argument of the inspect function is a record of fields with the following types: a caller field that has the principal value of the caller of the message, an arg value that contains the message's argument content in raw binary format, and a message field that is a variant of decoding functions, and this contains one variant per shared function and the ID of the actor. The inspect system function should not be used as a definitive form of access control, since it's executed by a single replica and does not go through full consensus, and it could potentially be maliciously spoofed. So if we take a look at the following inspect function example, this is going to deny all ingress messages and ignores all message information. So we're defining system func inspect. It takes a Boolean value, which can either be true or false, and in this instance, it is defined as false. In comparison, here's another inspect function example that declines all messages where the principal value is anonymous. So in this instance, we are importing the principal and bool libraries from the base library, and then defining the system function inspect, defining the caller as type principal, having it receive a Boolean value, and defining not principal dot is anonymous, and then pulling that caller value. So this is going to decline any messages where the value is anonymous. Messages can also be declined based on their raw size in bytes. So if their arguments prior to any decoding from the candid binary to the Motoko value exceed a certain amount, and we can define this as arg.size, and then define the size that we want it to decline if it is, in this instance, less than or equal to 512. Lastly, let's talk about errors and options. In Motoko, there are three primary methods for representing and handling errors. These are option values, which are non-informative null values that indicate that some error has occurred. Result variants, which are descriptive error values that provide more information about the error and what caused it. And then error values that can be thrown and caught in an asynchronous manner, similar to exceptions that contain a numeric code and a defined message. Some notes on error handling best practices. Motoko recommends that you use option and result error handling methods over exceptions whenever possible. This is because both option and result error types work in synchronous and asynchronous contexts, making APIs safer to use since it encourages clients to consider error cases along with success cases. It is recommended that exceptions are only used to single unexpected error cases. So taking a look at how to define error reporting with option values. If a function wants to return the value of type A or signal that an error can return the value of option type $A, the null value can designate the error. For example, if we have the following code snippet that defines a simple to-do function where you can mark a to-do item as done using the markDone function, then it returns an async value of seconds. So here we have public shared function markDone option. It takes the ID of the to-do item that you are wanting to mark as done, and then it uses a case statement to determine the current time and then calculate the amount of time that it took you to first create that item as a to-do item and then mark that item as complete. We can extend this code to use an error call site that uses a case statement where if we get a return value of null, it will reply something went wrong, or if it properly returns a value in seconds, then it returns congrats that took and then inserts the time stored in seconds to reflect how long it took you to mark that to-do item as complete. One drawback of this method is that since all possible errors return that single non-informative null value, then the only error that the user is going to get is something went wrong. They won't get a detailed idea of if something went wrong with obtaining the value in seconds, if the calculation went wrong, if the function was not called properly, etc. So that is one downside. And so one way to approach this from an alternative error handling perspective is to use result variants. These can return richer, more defined errors that provide better descriptions of what went wrong. Result variants are a built-in type that is defined as type result with OK and error, where the result can return either an OK value, which is a success value, or an error value. Result includes error type parameters, and so the result type allows you to select the type used to describe the error. So let's take a look at this snippet that expands upon our previous example using the simple markDone result function for marking to-do items as done. And in this, it uses result variants to signal errors. And so in this, we are including some code to return async result seconds to do error to allow us to return those errors. And then here in this case statement, we are defining the OK, so the success value as the seconds between result, and then using the second case value here as providing an error. And this one we are calling already done. So if we tried to mark an already done to do item as complete, we would receive this case error. And then if we get a null error, then we get this not found error. So then if we look at the call site for this code, we can see that the first error not found is going to return this text of there is no to do with that ID. And then this second error case is this already done error. And this is also going to define a new variable that calculates how long it's been since that error was already marked as complete. And then you're going to get this error message that you've already completed this to do, and it's going to insert that value of done ago to indicate how many seconds ago you already completed that error. And then if you get the OK success value, it's going to return that success message indicating that you have successfully completed that to-do item. So we can see that these errors are much more descriptive and clear than the errors we received here of simply something went wrong or the success statement. Here we can see that we can understand if the error was because the to-do was not found or if the to-do was already completed. Lastly, we're going to talk about asynchronous errors. This is a restricted form of exception error handling. Since Motoko error values can only be thrown and caught in asynchronous contexts, non-shared functions cannot employ structured error handling. A shared function can only be exited by throwing an error value and then trying to call a shared function on another actor. If the shared function returns an error type, the failure is caught. This error handling cannot be used in regular code outside of an asynchronous context. Asynchronous error handling generally should only be used for catching and signaling unexpected, irrecoverable errors, such as things that would cause the canister to trap. If a failure can be handled by the caller, it should use the result error types instead. So here we can see in our public shared function called markDoneException, we are having it defined as type async. And then in our error handling, in our case statement, we are using this throw error.reject already done. And so we are using this done indicator to indicate that the error is because the to-do item has already been marked as done. And then for the value of null, we are throwing error.reject not found. And then the call site for that looks very similar to the call site for the option values, where we only have two possible results that are returned. First is the success result that includes the amount of time it took to complete the to-do in seconds. And then we just have this catch E, and this is just something went wrong. So this is not as descriptive as the result variance, and as noted above, this is an error handling type that is restricted and should only be used in certain situations. It is highly recommended that whenever you can, you use the result error variance instead. That's going to wrap up today's episode. If you enjoyed today's video, please be sure to like and subscribe to the DFINITY YouTube channel. You can also check out the corresponding written tutorial for this video on the ICP developer documentation under the Developer Journey tab. You can stay up to date with all of the ICP developer updates on Twitter at DFINITYDev, or you can also follow the developer forum and the developer Discord server. Both of those are communities that you can interact with other developers on their developer journey. That'll wrap things up for today. Take care.